Okay, so I hope that clip got on the video because that was kind of humorous. I don't think it did. But it was humorous. What kinds of questions do you have? Yes. No problem.
Actually, 3.3.
Okay.
Just to understand what they mean, the numbers that are all behind the decimal, what numbers we classify the numbers in sequence as?
So this number has a definite pattern that you can ascertain. So the next digits are 1, 7, 1, 8, and so on. So the number is constructed by writing down the natural numbers in a sequence. The natural numbers are the counting numbers.
Okay.
The 14th digit would be, I don't believe they're counting the 0. I think they mean the 14th digit to the right of the decimal. Okay. Okay, thank you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1. The 25th digit, we're going to have to write it out further, and the 31st digit, you'll have to write it out further. But they do not count the 0 as part of the part of that. Oh, okay.
I thought they were natural numbers, but I thought maybe it was wrong, so I got confused, and then I ran out of attempts. So.
Oh.
No, I didn't run out of attempts. I was almost going to. So.
Oh, so you wanted to just make sure your last one was right.
Yep,
that's a good plan. Always bring those to class before you use your last attempt. Any other questions? Today we start in geometry in chapter 4. So for those of you who have been a little bit not so sure how you felt about the first chapters, this will be more visual, and that maybe will be more to your taste. I did write myself a note to remind you that on Friday, or maybe the following Monday, I never know how far we're going to get. On Friday, or possibly Monday after break, you'll need a few things for class. You'll need a ruler, a compass, and graph paper. So the compass is the kind of compass you draw circles with, like this, not the kind of compass that tells you north and south. The platonic solids then we won't need for sure until after break, possibly not for a week after break, but we'll know more as we're getting there. And like I said, it takes you a while to make the platonic solids, so plan that in your schedule sometime when you can sit and maybe listen to music or something while you construct those. .1 then, we start with a question from the author. A baseball diamond is really a square measuring 90 feet on a side. How far does a catcher have to throw the ball to get it from home plate to second base? Let's go ahead and take a look at that. Let's draw a square 90 feet on a side. And it's a square, so we put a little corner there to show that it's 90 degrees, a right angle. So the question is, how far does the catcher at home plate have to throw the ball to get it over to second base? So we're looking at this distance across. We'll call it D for distance. Who knows a way that we can find that length D? Anybody know? How can we find the length D? Yes?
Pythagorean theorem.
Yes, good. The Pythagorean theorem. Okay, now that you've heard it, the phrase Pythagorean theorem, who remembers what does it say?
Like do you want the
Yes.
a square plus b squared equals c squared?
Good. A squared plus b squared equals c squared in a right triangle. So a right triangle means it has a square corner, a 90-degree corner. Perfectly square, like when the floor meets the wall. Well, I've had some houses where it weren't perfectly square, but like our buildings here, the floor meets the wall, 90-degree corner. So the Pythagorean theorem works in reverse also. If you have a triangle and you're not sure if it's a right triangle, but you have a situation where a squared plus b squared equals c squared, then it is a right triangle. In fact, my husband does a lot of building, so he uses a famous Pythagorean triple sometimes when he's trying to make sure his corners that he's framing out are perfectly square, and he uses the triangle that measures 3, 4, 5. So the 3 squared plus the 4 squared equals the 5 squared. 3 squared is 9, 4 squared is 16, 5 squared is 25. And so 9 plus 16 is 25. So he can mark off 3 feet on this board and 4 feet on this board. This is where you want a big long square. You don't want to use your little tiny square that's just accurate for a little tiny bit. You want a big square. So I'll mark off 3 feet and 4 feet, and he'll have it lightly tacked. But then he takes his tape measure, and when that measures 5 feet on the hypotenuse, well, then he firmly tacks it, and he's got a nice, perfect square corner there. That's what he used to do. I think since then he actually bought a gigantic square, so he doesn't have to measure anything. But that's what he did when he first started out. All right. So well, let's go ahead and do that here. As you're doing this, remember the C is the hypotenuse. That's the longest side. It's the side by itself. So on the 3, 4, 5 right triangle, this is the hypotenuse. The longest side has to be the side that's C, otherwise you're not going to get a correct equation here. So the A and the B can be any, A can be B or B can be A, but C has to be by itself. So in this picture, the right angle is formed by the two sides that are 90. So those are the A and the B. They form the 90-degree angle. So 90 squared plus 90 squared equals D squared. We'll go ahead and find what D is. So 90 squared, that's 8,100. So altogether, it makes 16,200. Then you take the square root of both sides of the equation to find that missing length, D. So we get 127.28 feet. So remember the rule for rounding off. I'm going to round to hundredths place. So just go ahead and round to hundredths place, just standard. If you go on into a science class, they'll talk about significant digits and such. But we'll just stick with hundredths place for final answers. Anyway, if you're rounding to the hundredths place, the second decimal place, then the thousandths place is where you look, and if that's 5 or above, you round up. So my thousandths place is a 9, which is 5 or above, so I round the 7 to an 8. That's just saying you're closer to 0.27 to 0.28 than you are to 0.27. That's what you're saying. Okay. Why do we care about the Pythagorean theorem? Which was actually around before Pythagoras. For example, they found tablets with Babylonian Pythagorean examples on. So why would the Babylonians care? Why would Pythagoreans care? Why do we care about the Pythagorean theorem? Or any reason why we would care?
Erecting structures.
Sure. We want a nice square structure when you build it. When you build something, you want it to come out straight usually. Okay? So if you want it to come out straight, then your Pythagorean theorem is the place to go. Well, one of the tasks today then is to become proficient at finding missing sides of right triangles. So let's go ahead and try a couple of these. Here, let's try the one, hopefully you brought your 3x5 cards with that are made from the template made to work with today. So let's try one of those. So you took a 3x5 card. So it's 3 inches here, 5 inches here, and then you cut it on the diagonal to make a right triangle. Let's find the missing side X. Then we can even verify it by using a ruler on our card. If you just brought the template and didn't cut it out, at some point you can come and get some scissors and cut it out, okay? So, which one of these sides is the hypotenuse for this?
X.
Good, yeah, X. So X is not part of the right angle, it's opposite that. So X has to be by itself. So the X squared equals 3 squared plus 5 squared. X squared is 9 plus 25. X squared is 34. So we take the square root of both sides of the equation. The square root of 34 would be the exact answer, but we're going to see what it is approximately so we can compare on our ruler. So the square root of 34. 5.83. So if you need the exact value for some reason, then you would use the square root of 34. If you want the approximate value, that's what the little squiggly equal sign means. And then we can round it off. And you can take out your 3x5 card, and if you have a ruler, see how that worked out. So my templates, you can see they're 3 inches by 5 inches, and then the diagonal is, so it comes out to right about here. So 3.75 would be right here, a little bit bigger than 3.75. Okay. Well, we just talked about a 3, 4, 5 right triangle. Why wasn't X 4? I mean, we have 3 and 5. Shouldn't X be 4? Why wasn't X 4? Yes?
Well, it's different. The 5 and the 4 are not in the same place. Like that example you showed, the 4 was like a side or a leg. Not
Good.
a hypotenuse.
Exactly. Yeah. So here, the 5 was the hypotenuse, and here the 5 was a leg, A or a B. So yeah, very good. And that's why you have to make sure your hypotenuse is by itself when you're doing your Pythagorean theorem, so you do get correct answers. This 3, 4, 5 is a famous Pythagorean triplet. So Pythagorean triples are integers that make the Pythagorean theorem true. We find lots of numbers that are irrational that make the Pythagorean theorem true, but to have Pythagorean triplets, those are kind of special and interesting. Does anybody know any other Pythagorean triples? We think so. There is one with a 12 and a 13, and let's see if I wrote it down. It's a 5 though. It's 5 with it, yeah. 5, 12, 13. Did someone know another one? (8, 15, 17). If you're interested in Pythagorean triples or number theory, you can look up Pythagorean triples in Wikipedia, and it'll tell you how you can generate Pythagorean triples. They actually go on forever. Wikipedia is a good source for mathematics. I don't know if it is in all areas, but mathematics comes out pretty good there usually. Okay, well that was one example. Let's get another example. How about we find x in this picture? So the hypotenuse is 18, the base is 7. Oops, I told you what the hypotenuse was. I was going to make you figure that out. Okay. All right, so hypotenuse is over here by itself. The base is 7. So we'll have 7 squared plus x squared equals 18 squared. Always make sure the hypotenuse is alone. So 7 squared is 49. 18 squared, what is that? 324. This time we have a little arithmetic to do. We have to subtract the 49 from both sides of the equation. So 324 minus 49. 275. And then we'll take the square root of both sides of the equation. $16.58.
So would you rather have a decimal answer than like an independent number with square root?
So in my class, either one's okay.
Okay, so like we could have 5 square root 11.
Oh, that's nice too. That's fine too.
Okay.
So any of these three. Okay. Any other questions? Okay. Then I'd like you to try one. Let me try flipping this so that it's not so similar to what we just did. Can you find x, please? And I'll come around and see how you're doing. If you're stuck, raise your hand.
Yeah, this is the little square corner. Which one would be the hypotenuse? So the square corner is connected
So the square corner connects A and B. So we have the x squared plus the 12 squared go together. And then the one that's not with the square corner is the hypotenuse. So this came out to be a Pythagorean triple, but it's actually a multiple of the 3, 4, 5. We have 9, 12, 15, which is the 3, 4, 5 multiplied by 3. So you can always make another Pythagorean triple by multiplying one that you already have. And, then it's not an original Pythagorean triple, it's like a multiple of one. But we don't have to worry about that. Besides being able to find the missing side of a triangle, I'd also like you to be able to prove the Pythagorean theorem. So most of your friends remember the Pythagorean theorem. After today's class, you'll be able to prove it to them. So remember, I asked you to learn proofs so that when you are learning how to make your own proofs and to make your own arguments that are accurate and correct and unassailable, that you'll have some techniques learned to do that, and that you'll have some practice in formulating these arguments. These are formulated quite differently than some of the other proofs we've done, because the Pythagoreans and others who prove this would almost certainly have thought of a squared and b squared as c squared as actual geometrical squares. So if you take a square and you find its area, who knows the area of a square? How do you find the area of a square? Yeah, length times width. Someone said that. So if you have a square a by a, then you have a times a, or a squared. So this shape, a squared, is what the Pythagoreans would have thought of as a squared. Babylonians as well. Algebra came along many years after geometry did, thousands of years. So b squared would be a square b by b, and c squared would be a square c by c. So when we say a squared plus b squared equals c squared, what the ancients would have meant, and what we can think of it as, is areas. So these two areas, not these two particularly, because I didn't try to draw this to scale, but the squares that are shaped a by a and b by b can be rearranged and cut up and fit together to fill in the square c squared. So these have the same areas. So if we had done these to scale and we had made this 3 by 3 and 4 by 4, for example, and 5 by 5, then we could cut up all these little 9 squares that would have resulted in these 16 squares that would have resulted, and filled them into here to be 25 little squares. So we're going to look at proofs. We'll look at 3 proofs, and then your goal will be to learn one of them. So hopefully one of the 3 will click for you, and you'll be like, okay, that's the one that makes sense to me. That's the one I'm going to remember. That's the one I'm going to maybe put on my 3 by 5 card. Now there's many, many more proofs than 3 for the Pythagorean theorem, just because it's kind of fun to work. Does anybody know a president who used to study mathematics and who has a published proof for the Pythagorean theorem?
Wait, no.
Who?
Not Abraham Lincoln.
I don't.
He used proofs, but I didn't see anything.
he was Abraham Lincoln was good at geometry. Who do you think it was? Yeah, that's who you're thinking too. He was good at geometry, but it was actually James Garfield who published his own proof. And then, how about a famous artist? That might be easier. Any art people in here who might know what artist he would? This particular artist would spend a hard day working on his artwork and then go home and relax with some enjoyable mathematics. Who would that be? Does someone come to mind maybe who might be that kind of person?
Da Vinci?
Yeah, Leonardo da Vinci. That was something he did. Now his proof is very beautiful, and but it's got about 20 steps in it. So we're not going to do his proof. We're going to do a couple of simpler ones. If you have graph paper, this would be the time to use the graph paper. I will print graph paper on your quiz so that it's easier for you to fill in. The first proof we're going to look at, we're going to build some squares using your templates here. So these were 3x5 templates. Let's go ahead and label them so that we can all talk about the same sides the same way. Where is my graph paper? You'll probably need about 10 sheets of graph paper total throughout the semester, so if you want to print some off from the internet, that'd be great. So label your templates A on the long side of the right triangle, B on the short leg, and C on the hypotenuse. So I should have said the long leg. A on the long leg, B on the short leg, and C on the hypotenuse. And then all of our sides will be labeled the same. So I just picked A randomly to be the long side so that we can all be consistent and have A as the long side, B as the short side, and C as the hypotenuse. Now as you're working with these, you might decide you want them with you on your quiz, and that's certainly fine as long as all that's labeled on them is A, B, and C. Did anybody figure out how this square's shape, how the square's lengths related to the lengths A, B, and C? Did anybody figure that out as you were working it? Well, think about that. I'll ask you again in a little while. If you didn't figure it out, we'll talk about it again later. So our first proof, we're going to go ahead and make a big empty space that's C squared. So to make a big empty space that's C squared, we will put the C in the middle. And I want it to be C by C, so I'm going to put the length C on the outer edge. Now all the sides of this shape are C. That doesn't mean it has to be a square though. You could have a diamond shape that has all the sides C, all the same size lengths. The reason we know this is a square and not a diamond shape comes from these two angles. Why do I know these two angles together leave an empty space of 90 degrees? Does anybody know? Or phrase it another way, how do I know these two, the yellow little angle and the green little angle, otherwise known as acute angles, how do I know those add up to be 90 degrees and not 110 degrees or 83 degrees or some other measure? Anybody know anything about the angles in a triangle?
Oh, don't they all add up to 180?
Yeah, they all add up to 180. So these yellow and green triangles each have a 90-degree angle right here. And these two angles add up to 90 in the yellow triangle, and these two angles add up to 90 in the green triangle. Well, the yellow triangle and the green triangle are the same, and this angle up at the top here corresponds to this yellow angle right here. So once you take away the 90-degree angle, that leaves 90 degrees left, and that's why we know this is a 90-degree angle in here and not some other shape. Okay, so what we're going to do is draw this on paper. Let's draw it on graph paper as best we can. So I think we'll go ahead and make a littler version. I wonder if I can pull this down and put some graph paper up there and try and keep both on the screen. I'll give that a try. Okay, so we're going to start proof 1. I'm going to try and transfer this drawing up here only littler because that's too big. Okay. So I'm going to make a triangle that's 3 by 4. Okay, so my orange triangle, I'm going to make 3 squares across and 3 squares down. Now, if you don't have graph paper but you have lined paper, then use another piece of lined paper as a ruler. Okay, so make 4 lines tall, and then take another piece of paper and make 3 lines across. Okay, so you can still be accurate even if you don't have a ruler with you today. If you don't have a ruler, you can use your ID as a nice straight edge. So your ID makes a lovely straight edge, and then that'll make everything nice. Okay, so so I made that 3 wide and 4 tall, and the long side 4 is my A, and the short side B. The short leg is B, the long leg is A, and the hypotenuse is C. So there's one right triangle. And then I have another right triangle here at the bottom. So that time this time the short edge is vertical. So I'll make that 3. So the A, B, and C stand for any right triangle. But as I'm drawing, I want to make the right triangles all the same so that it makes sense in my picture. But we label A, B, and C instead of like 3, 4, and 5 because we want these to stand for any right triangles. So we have our A, B, and C, another A, B, and C, and another one, the green one now. So on the green one, the short side is down, the short leg is down, and the vertical leg is longer. One more triangle to go. I guess we could have started with the square and drawn the square out into triangles. So look at your drawing and verify that you have right triangles and that the long leg is labeled A and the hypotenuse is labeled C. So you see how the big empty space in the middle is C squared then? Okay? This big empty space is C times C, or C squared. Now we're going to make another set of squares that are A squared and B squared. We're going to form them with as an empty space. So before we draw them on the paper, let me form them with my triangles. So I'm going to make 2 rectangles, a vertical rectangle and a horizontal rectangle. I'm going to imagine these lines that I'm drawing, that I'm laying pens down to imitate. So the pens encompass a square. The dimensions of the square are dictated by the triangles that we laid down. There's a little square right here. What are the dimensions of that square?
B times B.
Yeah, B times B, good. There's B here and a B there. And how about on the big square? What are those dimensions?
A times A.
A times A, yeah. So this is the other picture that we're going to draw. So we'll draw it next to the one we already drew. We'll draw it a little bit off to the right. So we'll draw these two rectangles to correspond with our picture that we already drew. We'll draw rectangles 3 by 4. Okay, so 3 by 4 units and then cut the diagonal on them. Okay, so 3 units tall and 4 units. Oops, my vertical one is 4 units tall and 3 units wide. 4 units tall, 3 units wide. So the proofs not only help you to become good at making proofs, they hopefully help you become good at recognizing when someone leaves something out of their argument with you. So you can be like, no, you're missing something or other. Okay, and you can be correct. Okay, so there's my yellow and green triangles, and now I'll draw the horizontal rectangle and slice it on the diagonal. So we have our 4 triangles. We can make those right triangles and label them A, B, and C. So we'll put the A on the long leg, the B on the short leg, and the C on the hypotenuse. Okay, now that we've sketched that, I'm going to take these off and make it bigger. So let's extend the rectangles into forming a square. Like we did with pens. So you saw that this square is b by b or b squared, and this square has dimensions a times a or a squared. So I have these two, actually we have 3 big squares if you look at both drawings together, a c squared, a squared, and a b squared, and lots of triangles. Now, what is the length of this base and the height of this first square? What is its length and its height? Yeah, a plus b. So that first square is a plus b times a plus b for its area. So you take a plus b times a plus b for length times width. Well, that can be written as a plus b in parentheses squared. What about this second square that we sketched? What is its length and height, or width and height?
A plus B.
Good. It's also a plus b times a plus b, because here's the a up there that tells you this is a, and here's this b tells you this is b, and this a tells you this is a. So this is also a plus b times a plus b for area. So these two areas are equivalent. They're both a plus b squared. So we'll put an equal sign to show they're equivalent. Now let's write out how they're composed, okay? The two areas are composed of, this one is a big square, c squared, plus these 4 triangles. The second square that we drew is a squared plus b squared plus the 4 triangles. Now somehow we want to indicate that the 4 triangles are both, they're all the same. So off to the side, do you remember how you find the area of a triangle? Yeah. So the area of a triangle formula is 1/2 times base times height. So we'll just indicate that these 4 triangles in both of our pictures are the same by indicating their areas. Okay, so we'll say this is c squared plus 4 times 1/2 times, let's see, the base was b and the height was a. Same thing over here. We have a squared plus b squared plus 4 times each triangle, or 4 times 1/2 times base times height, which was a. So both of these figures are the same area. And we can go ahead and take away the 4 equal triangles from both sides. You could write that down, subtract the 4 triangles. And that leaves c squared equals a squared plus b squared. If you want, instead of writing subtract 4 triangles, you could say minus 4 times 1/2 times b times a. That's actually the same as 2 times b times a. So you can use the algebra, or you can just use the words there and subtract the 4 triangles. So this is one proof. You see how we get the Pythagorean theorem from that. The one square and the other square are the equal squares, and they're comprised of 4 triangles plus this other shape. When you take away the 4 triangles from each, what's left has to be the same, because you started out with the 2 quantities being the same. So that is proof 1. I had a lot of drawing going on. We're going to look at another proof. Does anyone have questions first? Okay, let's look at proof 2. So proof 2, we build a square that is C on the outside. So before I did C on the inside, now we're going to put the hypotenuses on the outside. I'll make this small so that we can fit it in here. Okay. So we put C, 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 and C. And once again, we're using the angles, the 2 acute angles in a triangle to form 90 degrees, because these are all the same size triangles. So when you take away the 90-degree corner, the remaining 2 quarters add up to 90 degrees, and that's what they're doing there on the corners. So we get a square. Okay, this square that you have in your template fits perfectly in here. Did anybody figure out how that length is related to the lengths of A, B, and C? Well, you can write it on here, because what it is it's the length A, the long leg, minus the length B, the short leg. So if you ever want to make another set of templates that have different size right triangles, you can. Just make your square to be the long leg A minus the short leg B. And you see how the short leg plus that little square makes the long leg? Okay? So I would write that A minus B on there. Then you'll have it if you need it for your quiz proof. Okay, so this is the drawing that we're going to use, and this drawing is the only one we have to draw, but then there'll be a lot of algebra with this one. So if you're an algebra person, this might be the proof you like. So let's transfer this. I think this one's easier to draw if you start with a square. So I'm going to start with a square that's 8 units by 8 units. So making 8 units by 8 units here. Once you have your square, your straight edge can help you draw these little triangles. So once you have your square, let your straight edge act like one of the triangles. See how it can have one edge go through each corner like that? So now my ruler is acting like the orange right triangle there. So your ID or your straight edge. Now I don't have a perfectly square corner on my ruler, so I'm going to have to stop a little bit away. Okay. So your ruler or your straight edge can go through both corners and be the triangle. And I'll turn it to be the yellow triangle here. Once you get the first one done, the others are a little easier. So you let your ruler or your straight edge go through both corners. I'm going to have to pull this down to fit down here. Well, I'll do it last. I'll do that one last. If it doesn't come out perfect, that's okay. That's the whole point of labeling all these right corners and putting the A, B, and C down. That's to show that, okay, it's not quite perfect in my drawing, but this A is supposed to be that size of that A, and this B is supposed to be the size of that B. That's why we label it in the math. Besides that, it makes it a general square, not necessarily an 8 by 8 square. So we have C on the outside edges, A on the long legs, B on the short legs, and importantly, the inner square is length A minus B times A minus B. So now I have that drawn, I'll make it larger. So this proof uses a lot of algebra. We first notice what we have going on. We have c squared equals 4 triangles plus 1 square. So we are approaching this geometrically, so we write down what the area of the 4 triangles and the 1 square is. So the c squared is the 4 triangles, which we already noticed their area is 1/2 times A times B. And now we have a square in the middle. So the square in the middle has length A minus B times A minus B. So we just have to do a little algebra on the right, and we will have our Pythagorean theorem. So the c squared is 4 times a half, that's 2, times A times B. And then the A minus B times A minus B, we're going to use a little algebra called FOIL. Who remembers the word FOIL from their youth? For some of you, that wasn't very long ago. Some of you are very young. All right. FOIL stands for first, outers, inners, last. So first would be A times A, so A squared. Outers would be the A times the negative B, so negative AB. Inners would be a negative B times A, so that's a negative AB also. And last stands for the negative B times the negative B. So negative times a negative is positive, so we have positive B squared. Well, on the right then, after you use FOIL, you have a negative AB and a negative AB. Those add to the 2AB to cancel. Okay, so this is like a negative 1AB and a negative 1AB, so those combine with the 2AB to cancel. And what we have left then is the Pythagorean theorem. So that's proof 2, and if you're an algebra person, that might be the proof that you prefer. We will look at one more proof on Wednesday, so please bring back your materials that you've used today. I'll see you then. Does anyone have any questions? Okay.